In this lecture, we are going to discuss on non-ferrous metals and alloy. In the last lecture, we have discussed on ferrous metals and alloy, and in this lecture, we are going to discuss some of the important non-ferrous metals, alloys, their structures. So, objective of this lecture is first we are trying to discuss on what are the limitations of the ferrous alloys, and then we are going to discuss on aluminum and its alloys, titanium and its alloys, copper and nickel alloys, and finally some super alloys, nickel based super alloys. Now, limitations of ferrous alloys is mainly relatively high density. Ferrous alloys are generally of high density and relatively low conductivity. If you compare with respect to others like aluminum or copper, the ferrous alloys are respectively low conducting materials. And the major disadvantage of the ferrous alloys, the poor corrosion resistance. That means they corrode very easily, they rusted very easily. So as we have already seen that the metals alloys can be divided into two broad categories, ferrous and non-ferrous. We have already discussed in one of the earlier lectures on ferrous metals and their alloys, that means steel and cast iron. Now in this lecture our objective is to discuss on non-ferrous metals and their alloys. Specifically, again this non-ferrous can be divided into light alloys and heavy alloys, and in the light alloys category, as you can see, aluminum, zinc, titanium, they are basically light metals and their alloy. And heavy alloy category, you can see copper, nickel, cobalt, they are heavy alloys. That means their density is high, and their alloys that we are going to discuss. Okay. Now let us start with aluminum. As you can see that the crystal structure is FCC, melting point 660 degrees centigrade. If you compare with respect to steel, which was more than 1500 degrees centigrade, for cast iron, which is around 1200 degrees centigrade, you can see the aluminum melting point is quite low. Okay, density 2700 kg per meter cube. So it's a light metal if you can compare with respect to steel, which is the density is around 7500, 7800, like that. Okay, so quite low. Elastic modulus 70 gigapascal, and the appearance silvery gray lustrous metal, and high thermal and electrical conductivity is the main advantage of using aluminum and its alloys. Okay. So here you can see some of the important application, like in beverage can, aluminum wares, or the fins that you can see. Those are, since they are highly thermal conducting materials, so fins can be used made of aluminum and aluminum sheets. Okay. Again, if we can recapitulate that these are low density FCC, already discussed, high electrical and thermal conductivity. Aluminum is non-magnetic, not sparking, and it's insoluble in alcohol and water. Okay. Now the main advantage of using aluminum, it is highly corrosion resistance. Okay, the corrosion resistance can be excellent due to thin surface layer of aluminum oxide. So actually what happens at the surface of aluminum, there is aluminum oxide layers, and these aluminum oxide layers make the whole inner material passive with respect to the outside surface, because the further oxygen cannot penetrate into the material to corrode it further. So aluminum oxides actually creates a barrier to further oxygen infiltration into the material, and this phenomena is called the passivation. All the metal oxides do not have these properties. Okay, already we have seen that chromium oxide also having the similar kind of property, that create a barrier or resistance to further oxygen to penetrate into the material. Aluminum also having the same property. Okay, and it is easy to cast because of its low melting point. That is also advantage of using aluminum. Now, if we see advantage applications of aluminum, they are very highly ductile, so can be easily formed into different shapes. They are very good conductors of electricity and heat, and they are also cheap. So they are used in different heat equipments like heat exchangers and others. Electrical wires, aluminums are used. Aluminums do not have any aroma, and that is why they are suitable for food packaging. Aroma means kind of a smell. They do not have any smell of its own. That's why they can be used for the food packaging, food packing, in cooking pots also aluminums are used. In mirrors and decorative textural components, aluminum is also used. However, the application of pure aluminum is very rare as compared to its alloy. Why? The first point is definitely its low melting point. So high temperature applications you cannot use direct pure aluminum, right? And another one, they are very soft. That means the strength is not very high. So for high temperature application, pure aluminum is not suitable. Where we need sufficient amount of strength, like in automobile or aircraft applications, there pure aluminum is not suitable, and that's why it is required to alloying with other elements to make aluminum strong and to increase its temperature, melting point temperature, so that high temperature it can be used. The typical alloying elements for aluminums are copper, magnesium, manganese, zinc. Okay, two most important you have to remember. One is the duralumin. Okay, it's all aluminum copper alloy. Here you can see 95% aluminum and around 4% copper is there. Okay, some amount of manganese and magnesiums are also there. And magnesium, where basically the name itself tells you that it's a magnesium and the aluminum alloy, and you can see 70 to 90% aluminum, and it is around 30 to 10% magnesium which is present in magnesium. So these are the two most important aluminum alloys. Okay, one is aluminum copper alloy, which is duralumin, and another one is magnesium, which is magnesium aluminum alloy. Okay, now aluminum and its alloys are characterized by relatively low density. This is the main advantage, and that's why aluminum alloys are preferred. Low density, having strength almost equal to steel. So by these alloying elements, it's possible to increase the strength to a very high value. Resistance to corrosion. Okay, since aluminum having the property of forming aluminum oxide at the surface, so they are highly resistant to corrosion, and many of these alloys are easily formed by virtue of high ductility. Okay, because aluminum having very high ductility, so that thing can also be used. Okay, and tensile strength can be raised by heat treatment. Okay, tensile strength can be raised by heat treatment in aluminum alloys without sacrificing much ductility. So this is a great advantage of using the aluminum alloy. So high electrical and thermal conductivity definitely will be there in the aluminum alloys, and having excellent fatigue and low temperature toughness properties. As you know that if the temperature reduces, then material becomes more and more brittle and the toughness property reduces, but aluminum alloys having excellent low temperature toughness properties. Another one, excellent fatigue. Okay, so they have excellent fatigue property. Aluminum alloys are widely used for aeronautical and the automobile industry, as you can see, and for electrical conductors. Okay, for household and consumers items such as utensils, for marine application, for surface transport such as fittings in railway coaches and buses. Aluminum is also used in making windows, doors, right? And also in sporting equipments, aluminum alloys are used. Now these are the important aluminum alloys. Already you have seen the duralumin. You can see the composition of duralumin: 4% copper and around 0.5% manganese, 0.5% magnesium, and the remaining is aluminum. Its properties: high strength, rather higher strength than steel, corrosion resistance lower than aluminum. Pure aluminum, the corrosion resistance is lower than pure aluminum, but still very good corrosion resistance. Here you can see the application, alkyd sheets in aircrafts and automobile industries. So these are the major application. Here you can see another alloy, which is the Y alloy. Y alloy where 93% aluminum and 2% copper, 1% nickel and magnesium. Okay, so these are again used in aircraft cylinder heads and piston in the aircraft engine. So these are also high strength alloys having good mechanical properties. Okay, and they heat treated in boiling water. Here you can see they are quenched in the boiling water. Now magnesium, already we have seen magnesium alloy, around 2 to 10% magnesium, heated and cooled in vacuum, used in automobiles and aircraft industry. Hindallium is also magnesium aluminum alloy, but a small quantity of chromium is also there, used in anodized utensils. Okay, so they are highly corrosion resistant. Now coming to the titanium. Here you can see for the pure titanium the density is 4500 kg per meter cube. Melting point is quite high, 1660. Elastic modulus 107 gigapascal. Tensile strength 150 to 500 megapascal. Appearance silvery grey white metallic luster. Alloying required to reduce cost, increase strength and control phase. Okay. Applications, high strength and temperature components, where the strength and temperature, high temperature applications titaniums are used. Biomedical applications titaniums are used, and jewelry titaniums are used. So titanium having a lot of applications. Two crystal form, below 883 it's alpha structure, and beyond 883 it's a beta structure, which is BCCM. So it is like if you consider in case of iron also, right, below a particular temperature a particular structure is there, above a particular temperature another structure is there, like alpha, like delta. Okay, similar here also. Now 4 alloys which are very very important for the titanium you have to remember. The alpha alloy, near alpha alloy, alpha beta alloy and the beta alloy. Okay, among them alpha titanium and alpha beta titaniums are the most important, but all of these are very very important. Titanium alloys are having a lot of applications in industry. So alpha phase stabilizers, that means if this aluminum, gallium or germanium, carbon, nitrogen, if these are the alloying elements, if you add with the titanium, then you will find that alpha phase will be stabilized more, whereas beta phase stabilizers are like molybdenum, vanadium, tantalum, niobium, manganese, iron, chromium, cobalt, nickel, copper, silicon, like this. Okay, so they basically stabilize the beta phase. Okay, actually what is done in these alloys, basically sometimes some combination of alpha stabilizer and beta stabilizer are used, and this intermediate like near alpha, alpha beta, these are produced. Okay, so let us see one by one what are their different applications. First of all, alpha titanium alloys. So definitely alpha stabilizers are present here. Low, medium strength, good notch toughness. This is the property for the alpha titanium alloy. Remember, good notch toughness and reasonably good ductility, and that is why the toughness is very high. Excellent mechanical properties at cryogenic temperatures. That means at very very low temperature, excellent mechanical properties are there. Okay, and non-heat treatable and generally very weldable. So that is also an advantage of this kind of alpha titanium alloys. One of the example is given, titanium where 8% aluminum, 1% molybdenum and 1% vanadium. So tensile strength in the order of 950 megapascal and used in jet engine components. Okay, alpha titanium alloy. Now near alpha titanium alloy, like besides alpha phase stabilizer, near alpha alloys are alloyed with 1 to 2% beta phase stabilizers. Okay, so offer high temperature creep strength and oxidation resistance. So these are very important properties for the high temperature applications. Okay, so creep strength, already I told you that at very high temperature applications, generally what happens, time dependent deformation of the material occurs without increasing the stress. Okay, so this phenomena is definitely not desired for different engine parts or the components where the high temperature exposed. So titanium 6, aluminum 2% tin, 4 zirconium, 2 molybdenum. The tensile strength is in the order of 1100 megapascal and used for creating high temperature jet engines components and high performance automotive valves. Okay, so this is what is the near alpha titanium alloy. What you have to remember, you basically have to remember what are their important properties and their applications. So applications you have to remember. Now alpha beta titanium alloys, these are metastable and generally include some combination of both alpha and beta stabilizers. Weldable with the risk of some loss of ductility in the welded area. Strength levels are medium to high. Hot forming qualities are good, but cold forming often presents difficulties. Okay, creep strength is not usually as good as in most alpha alloys. Okay, example like titanium 6%, aluminum 4%, vanadium. Tensile strength in the order of 940 megapascal used where low density and good corrosion resistance is necessary. Okay, low density and good corrosion resistance. So it is highly corrosion resistant, that is very important, such as in aerospace industry, a lot of application is there of this alloy, and in bioimplants, prosthetic and prosthesis application, these are used. Remember, for the bioimplants, these titanium alloys are used. Now beta titanium alloys, the metastable and which contains sufficient beta stabilizers. Okay, fully heat treatable, generally weldable, capable of high strength, possesses good creep resistance up to certain intermediate temperature. Cold formability is generally excellent. Titanium 10 vanadium, 2 iron, 3 aluminum, you can see, and tensile strength in the order of 1200 megapascal, used for critical aircraft structures such as landing gears. Okay, so you have to remember some important applications of different titanium alloys. Now coming to the zinc, the crystal structure is HCP, melting point 420 degrees centigrade, quite a low melting point, you can see, even lower than aluminum. Density is 7140, silver gray lustrous appearance, easy castability. Okay, applications: galvanic coating on steel. Already we have discussed that galvanic steel sheets are used. They are highly corrosion resistant because the zinc coating is given over there. Okay, either by hot dipping or by electrolysis. Corrosion protection of structures by attaching as sacrificial anode. Okay, so actually what happens, this zinc coating on the surface of steel acts as sacrificial anode. That means when some corrosive environment that steel is exposed, then if you compare between zinc and the iron, that means the steel over which the zinc coating is given, suppose a particular portion has been scratched. Okay, that means the coating is peeled out from the surface. Then the steel surface is also exposed to the oxygen. Now the oxygen will react with the zinc at a higher rate with respect to the iron. So what happens, the whole zinc layer will corrode very easily and corrode very easily, but the oxygen will not actually react with the steel, because zinc in the electrolysis series is at a higher position. That is why zinc will react more vigorously with oxygen, and that is why it sacrifices itself and save the inner material like steel. And then after that, what happens, again the galvanic coating is given on that steel. So this is what is the procedure by which it saves the inner material. Okay, so this is what is the galvanic sacrificial anode is used by zinc coating. And also you know that zinc carbon battery, dry battery is used. And naturally zinc is also very important for our body, and you know that a lot of disease may occur because of the deficiency of the zinc, like diarrhea, pneumonia, slow brain growth and all that. And there are many foods naturally we get zinc, like spinach, cashew, seafoods, like that. Now coming to the copper. Copper, you can see it is a FCC structure. Melting point is around 1100 degrees centigrade. Density is 8920, rather more than the steel, which is close to 787900. So copper is higher density than steel. Distinctive reddish orange color that you can see. Good corrosion resistance. Copper having very good corrosion resistance. Soft, malleable. Malleable means they can be made very thin, okay, by application of force. It is very ductile, highly ductile material, copper, and very tough material, okay. Good machinability and high electrical and thermal conductivity, okay. Thermal conductivity, if we just order between silver, copper and aluminium, the thermal conductivity of silver definitely is highest, but after that it is copper and then it is aluminium. But 99.99% pure copper used for wiring applications, okay. For wiring application, 99.99% pure copper are used, and possesses around 97% of the conductivity of the silver at 1/8 cost. This is one of the major advantage of the copper over silver. It's 97% of the conductivity of the silver, but the cost of copper with respect to silver is 1/8. Now copper alloys. Copper alloys are basically two main alloys. One is brass, another one is bronze. Okay. So first brass. What is brass? Brass is basically the zinc. So copper, when mixed with zinc, it is called brass. Okay. The main substitutional impurity of that is zinc, and up to 45% purity is there in brass. Okay. Other than tin, aluminium, silicon, magnesium, nickel, lead may also be added. As zinc content increases, the strength, hardness, ductility increases, while the conductivity reduces. Okay, with respect to the pure copper, definitely its strength, hardness, ductility increases, but the conductivity reduces. Commercially used brass is divided into two categories: alpha brass and alpha plus beta brass. In alpha brass, here the zinc percentage is up to 30%, and in alpha plus beta brass, the zinc percentage is more than 30%. But in brass, maximum it is up to 45%. That means in alpha plus beta brass, it is 30% to 45%. Okay. So in alpha brass, there can be different types of alloys, and depending upon the percentage of zinc present, like gunmetal, up and they are around 2% zinc. Okay. Where gunmetals are used in bearings, bushes, gliding metal, 5% zinc. Where it is used, coins, medal, jewelry. Admiralty brass. Admiralty brass is 28% zinc. Okay, 1% tin. Used in condenser, evaporator, and heat exchanger tubes. So very important. Admiralty brass. Okay. Cartridge brass, 30% zinc, and ammunition cartridge cases, automotive radiators, lamp fixtures. These are the applications of the cartridge brass. You remember, okay, in the radiators, radiator tubes, this brass is used, cartridge brass. Alpha plus beta brass, where more than 30% zinc is present, it's like Moon's metal and naval brass. In Moon's metal, used in valve stem, architectural works, it is used, and naval brass is used in marine construction, propeller shaft. Okay, 39.25% zinc and 0.75% tin. So you have to remember these important category of the brass and their application. The applications is very important. So questions may ask that what is the material used in medals? Okay, your answer may be only brass, but it will be better if you can remember it is the gliding metal, alpha brass. Okay. Now another kind of copper alloy other than brass is the bronze. Okay, so in case of brass, what was their alloying element? Main alloying element was zinc, right? In case of bronze, it is the tin. Okay, so tin is the main substitutional impurity that is there with copper. So possesses superior mechanical properties and corrosion resistance even more than that of brass. Okay, so highly corrosion resistance and mechanical properties, superior mechanical properties, comparatively hard and resist surface wear. Okay, commercially used bronzes are phosphor bronze. You have to remember that 10% is tin, 1% phosphorus is there. So phosphorus improves castability, used in music instruments, springs. These are used, phosphor bronze. Okay, for musical instruments, phosphor bronze are used. Ammonium bronze, 11% ammonium, 3.5% tin. Okay, so higher strength and corrosion resistance as compared to other bronze alloys. Okay. It is used in bearings, landing gear components in aircraft. Silicon bronze, 3% silicon is there, up to 3% silicon is there, and self-lubricating, high strength and toughness in bearing gauge. Other important copper alloys other than bronze and brass, it is beryllium copper or German silver. These two are also very important. So highest resilience you will get in beryllium copper, around 3% beryllium is present, used in spring. You know, to make spring we need highly resilient material, so beryllium copper having that. In screwdriver, pliers, wrenches, this beryllium copper can be used. German silver, it is 60% copper, 20% nickel and 20% zinc. Okay, remember there is no silver in it. Silvery appearance but no silver. Nickel increases electrical resistivity, improves strength and corrosion resistance. Where it is used? German silver, condenser tubes, cutlery, there German silvers are used. Now coming to the nickel, crystal structure is FCC, melting point 1455 degrees centigrade, very high melting point. Density 8900, similar to copper. Silvery, white lustrous metal with slight golden color. Applications: nickel metal hydride rechargeable batteries, that you know, nickel hydride batteries. And the main alloy of the nickel is the monel metal. Okay, monel metal is a nickel alloy. It is basically nickel and copper, primarily composed of nickel and copper with traces of iron, manganese, silicon, carbon may also be there. Strong corrosion resistance, and heat exchanger tubes are made of monel metals. Okay, food processing plant, marine application, mainly marine applications. So this is very important. In marine applications, you have to remember, this is very important. Monel metals mainly used in marine applications. Okay, then nickel based super alloys, these are highly creep resistance and oxidation resistance and used for very high temperature application where chances of creep is more, like in turbine blades. Okay, so nickel based super alloy. Let us see again the nickel copper alloys. Nickel copper alloys, these are called basically monels. Already we have seen monel metals, where nickel copper alloys contain 67% nickel, 33% copper. You remember that nickel copper alloy from complete solution. If you remember, we have already studied isomorphous phase diagram where copper nickel system is the isomorphous system. That means 100% solubility is there. Okay, so anyway, 67% nickel, 33% copper, called the monels. Okay, there are two types of monels. One is monel metal where consists 67% nickel, 33% copper, 2% manganese and 5% iron is also there, but mainly it's nickel and copper. High strength and toughness, good weldability, excellent corrosion resistance property. This is the main property for which the monels are preferred for the marine application. So corrosion in the seawater is very dangerous thing, and that is why selecting material for seawater applications is always a challenging one. And monel metal, highly corrosion resistance, and for the marine industry many components like pipes and all that are made of the monel metals. Okay, so this is a very important applications. Other than that, in steam turbine blades, since high temperature corrosion resistance property is there, high temperature strength is there, so high temperature valves, centrifugal pump impellers. Centrifugal pump impellers can also be made of monel metals. Remember, high temperature valves, centrifugal pump impeller, okay, steam turbine blades, and mainly in marine applications. K monel, where 66% nickel, 29% copper, small amount of aluminium, manganese, carbon is also there. They are non-magnetic, and aluminium increases strength and hardness. Okay, pump shaft, springs, and valve stems, they can be used. Now coming to the nickel-based superalloys, the superalloys can be strengthened by either solid solution strengthening or by precipitation hardening. Okay, so by precipitation hardening means the alloying elements are there, and those alloying elements may form certain second phase particles. Those are because of the solubility getting out of the material because of diffusion, and produces this kind of particles throughout the material. These are called the precipitation of the different alloying elements. Okay, so in this way they are creating the strain fields, and ultimately they strengthen the material. And another one is the solid solution strengthening. You know already, if you add more and more number of alloying elements, if you more number of alloying elements, if you add, it is maybe even a small amount, okay, that will create a huge amount of strain field, and ultimately the strength will increase. That is what is called the solid solution strengthening. So both solid solution strengthening and precipitation hardening. Precipitation hardening means that suppose if the solubility decreases of a particular material with the temperature, then what happens? Maybe supersaturated solution when come to a lower temperature, and if you allow it there for a long time, gradually the extra amount that was at a supersaturated condition, that will come out and precipitate in the material as different particles, and those are going to create a strengthening the material. So this is what is the precipitation strengthening. So most nickel based alloy contains 10 to 20% chromium, 8% ammonium and titanium, 5 to 10% cobalt, small amounts of boron, zirconium and carbon. So you can see that many different kinds of alloying elements are added, so that solid solution strengthening can be very high, or the precipitation hardening will be very high. So these are very important, because at a high temperature application where the chances of creep is very high, like in gas turbine blades, there the solid solution strengthening and precipitation hardening is the most effective way of making the material hard and keeping its hardness at a very high temperature. Because all other methods of hardening that you have seen, like heat treatment or by fine grain size, those are not applicable for the creep resistance. Okay, so at high temperature creep resistance, these kind of hardening methods are not going to resist the creep. So to make the material creep resistance, it is required the solid solution hardening or the precipitation hardening, and that is why this kind of nickel based superalloys, where many alloying elements are added, okay, but the chief alloying element definitely is the nickel, and along with chromium and other, which can retain its hardness at a very high temperature by either precipitating those alloying elements and by solid solution strengthening by different alloying elements. Okay, so other common additions like molybdenum, rubidium, tungsten all plays the dual roles as strengthening as a solute and carbide formers. Okay, so different alloying elements, what they do, they basically forms the carbide, and those carbides basically precipitates, and those carbides are hard and they precipitate and create the increase the strength of the materials. Okay, chromium and aluminum improves the surface stability through the formation of chromium oxide and aluminum oxide. Since chromium and aluminum is present, so they definitely increase the corrosion resistance by forming chromium oxide and aluminum oxide, already that we have discussed. So this nickel based superalloys having applications where you can see some of the applications of these superalloys. Here you can see the turbine blades and jet rocket engines. pressurized water reactor vessel head, where again the high temperature applications, rocket motor engine, where nickel based superalloys are used, very high temperature applications. You can see turbine blades for the jet engines or gas turbines. Okay, so now finally another one, which is the nickel chromium alloy, that is again the superalloy, one of the kind of the superalloy, which is Inconel 600, and this is a family of austenitic nickel chromium based superalloy. Here you can see there are many alloying elements are added to increase the solution strengthening, and used at very high temperature, high corrosion resistance at high temperature, high strength and workability, difficult to machine. Applications like gas turbine combustion, combustors, blades, pulp and paper industry and soap manufacturing industries also can be used because of its high resistance to corrosion even at a very high temperature. Now another nickel alloy, which is the nichrome, you can see 80% nickel and 20% chromium. And as you know, nichrome having very high melting point and high electrical resistivity. Okay, so that is why they are used for resistance heating coils, rocket igniters, jewelry casting supports, ceramic manufacturing industries. They are used. Okay, mainly heating coils, you can see nichromes are used. Okay, in rocket igniters they are used because they are having very high melting point and high electrical resistivity, most important properties. Now another alloying element, we should not call it is a nickel alloy. Definitely nickel is a chief alloying element, and 64% iron and 36% nickel is there. Sometimes it is also called invar steel, because 60% it is basically iron. Anyway, so 64% iron and 36% nickel alloy. This particular alloy is called the invar, an excellent resistance through thermal expansion. Okay, so thermal expansion coefficient is very low. That means with the increase of heat or the increase of temperature, its expansion is very less. Okay, so excellent resistance to thermal expansion, and because of this property they are used to make different precise instruments, or they are used in thermostats as a bimetallic strip. One of the material is made of invar. Okay, so that means for a temperature sensor, like in thermostat, where bimetallic strip is there, where maybe one is highly having very high thermal expansion coefficient and another material is considered as invar. Okay, so for in those sensors this invar is used. So you'll find invar in electric iron toasters, computer screens, where basically the temperature sensors are present. It is basically the invar. This material is very useful, and it also prevents that stress corrosion cracking, as you can see. Okay, and invar is well level and very ductile material also. Thank you.